Suppose we want to know if this improper integral converges or diverges. Well, how do we do that? One way you can integrate this, because I think this is easy to integrate by using U substitution, but let me show you another tool that you can also use when you cannot integrate, but you can actually compare it to another function that you're familiar with, its convergence or divergence. So let's talk about the direct comparison test. Let's take a look at this picture. So I have this inequality where f happens to be below g of x. They're both positive. So we want to know what would happen as you integrate the following. So let's say we want to look at only this particular piece of this two functions. Let's say from some a, and I want to integrate this portion right here. So if you look at this function from a to infinity of f of x dx, well, that's definitely less than the integral from a to infinity of g of x dx. Now let's see what happens. So since f lies below g of x, that means that so we can write down two important statements. If you're integrating, if a is 1, so let's be specific, what is this a? If you're integrating from, let's say, 1 to infinity of this function f of x dx, and if this happens to diverge, then f is going to, then g, the integral from 1 to infinity of g of x, is also going to diverge. So that's what we can say, because if something below diverges, then whatever above it will also diverge. Or we can write down the following statement. If the integral from 1 to infinity of g of x dx, if that one converges, then if something above converges, then whatever lies below will also have to come to a finite value. It will also converge. Then we can say that the integral from 1 to infinity of the function that lies below will also converge, meaning you'll get to a number, a finite value, not infinity. So this is one big conclusion we can talk about when it comes to comparing functions. There are many other variations to this, but this is one that I think it'll be useful in many cases. It will definitely be useful on the example we're going to work out. Now, we do need some tools. We can't just think of f and g being any arbitrary functions. So one function you can always think of is this one. So we call it the p integral. P integral is the function of this form, 1 to infinity of 1 over x to the power p dx. So this integral has two different interpretations. So it's going to converge to a finite value if p is greater than 1. So if you're integrating from 1 to infinity of 1 over x squared, where p is 2, that's going to converge to some value. But if p is less than or equal to 1, then it's going to diverge. So this is one very useful integral that you can always compare it to for the most part. Sometimes you might not be able to, but it's a very nice tool to have when it comes to doing the comparison test. So let's go back to our example and see if we can compare it to this p integral. All right, so I want to know if this integral converges or diverges. Now, I don't want to integrate. I just want to use the comparison test. So let's see. So I'm going to break it up so I can use the p integral because I see that I have some variation of 1 plus x squared on the bottom. So I'm thinking of the p integral, but I need to make sure this limit of integration goes from 1 to infinity. So let's split it up. So this is the integral from 0 to 1 of 16 tangent inverse of x over 1 plus x squared, plus the integral from 1 to infinity, 16 tangent inverse of x over 1 plus x squared dx. Now this you can integrate. It's a finite integral. You can do it. This is going to be a finite value. That's good. Now what about this one? Well, now that's the big question. That's where I'm going to use the comparison test. So check this out. If you look at this function, 16 tangent inverse of x over 1 plus x squared, and let's say just 16 tangent inverse of x over x squared. All right, so let's take a look at tangent inverse of x. So we know that tangent inverse, the graph of that function looks like this. So you have curve that's approaching pi over 2 as x goes to infinity. And this is negative pi over 2. We have two horizontal asymptotes. So if we're only looking at the interval from 0 to infinity, then we're looking this direction. So we see that the graph is getting closer to pi over 2. So that means it will never be greater than pi over 2. So we can say that tangent inverse of x is not greater than pi over 2. So it's always going to be less than that. And then I'm going to put this inequality right here because this is 1 plus x squared, this is x squared. 1 plus x squared is greater than x squared. When you put that in the denominator, the fraction value becomes smaller. So that's the inequality we set up. Now let's go ahead and integrate this. So if we now try to integrate the left-hand side from 0 to, so we're looking at 1 to infinity. So this is 1 to infinity dx, and also this one from 1 to infinity dx. So if I can show that this converges, then that means the one that lies below will also converge. So let me see if I can work with this integral. If you simplify 16 and pi over 2, you'll get 8 pi times the integral from 1 to infinity of 1 over x squared dx. Now this is a p integral. That's the piece we always want to remember. Here, this is a p integral with p being equal to 2. So p is this power right here, 2. So because p is 2, which is greater than 1, this converges. So this integral is going to converge. And that's what we wanted. We wanted to make sure the one that lies above converges. So this integral, 8 pi of 1 to infinity of 1 over x squared dx converges. Therefore, we can conclude that this will converge since that lies below the one that lies above. So now we can make our final statement that this integral is going to converge. So that's the final statement for this integral. Here's another very interesting one. So we're looking at the integral from 0 to 1 of this function. We want to know if this is convergent or divergent. Okay, so I'm going to use the comparison test. So first I'm going to combine these. So I can rewrite the same integral as the integral from 0 to 1 of ln of x plus 2 over, so x times x to the 1/2, that's x to the 3/2 dx. Right, so let's use the comparison test now. So ln of x plus 2 over x to the 3/2. And I want to compare this with, let's say, x to the 3/2. And on top, I'm going to, let's see, I'm going to put just ln of 2. Because if I plug in 0 for ln of x plus 2, the lowest value I can obtain is ln of 2. And then when you plug in 1 into ln of x plus 2, that maximum will be at 3, ln of 3. So if you look at this expression, then, well, ln of x plus 2 over x to the third, x to the 3 over 2, this is greater than or equal to this function I just came up with. So if I integrate from 0 to 1, this inequality holds. So I'm able to come up with a function that is something that's smaller. So in other words, we're looking at the integral from 0 to 1 of some ln of 2 over x to the 3/2 dx. It's less than or equal to the integral from 0 to 1 of ln of x plus 2 over x to the 3/2 dx. So if I can show that this diverges, then whatever lies above will also diverge. So since I came up with something smaller, it has to diverge. Well, let's see. Will it diverge? Let's check it out. So it is improper at 0. So we're going to take the limit as some b goes to 0 from the right of the integral from b to 1 of ln of 2 over x to the 3 over 2 dx. So now this integral, we're going to be using the power rule of integration. So I'll just bring this on top, make it a negative exponent. So we're taking the limit as some b goes to 0 from the right of the integral from b to 1 of ln of 2 times x to the power of negative 3/2 dx. So we add 1 to the power, same power goes on the bottom. So if I do negative 3/2 plus 1, well, that will give me negative 1/2. So you'll have the limit as b approaches 0 from the right, ln of 2 times the integral of x to the negative 3/2. We just said that's x to the negative 1/2 divided by negative 1/2, which is same as multiplying by negative 2. So I'll just write it that way, taking it from b to 1. All right, so finish with the integration. Now let's do a little bit of simplification before we take the limit. So this is the limit as b approaches 0 from the right of negative 2 times ln of 2 over x to the 1/2, which is square root of x, and taking it from b to 1. So I'm just rewriting before I apply the limit. Now, apply the upper limit of integration. So this is the limit as b approaches 0 from the right, negative 2 times ln of 2 over square root of 1 minus negative 2. So that will be a plus. So I'm doing the lower limit of integration, plugging in b, using the fundamental theorem of calculus. So this is 2 times ln of 2 over a square root of b. All right. So now if you take the limit, well, this is a value. So that's a finite number. So we have negative 2 ln of 2 over 1. But now if you take the limit of the expression right here, so you have the limit as b approaches 0 from the right of 2 ln of 2 over square root of b. Now, as you get closer to 0 from the right, this whole thing, it's actually going to go to infinity. So this whole thing is actually going to diverge. So this is going to get closer to infinity. So therefore, this whole thing is going to diverge. So what does that tell us about our integral? Well, we found something below the one we're looking for, and it diverges. So because something below diverges, whatever lies above will also diverge by the comparison test. So therefore, we can conclude that this integral diverges.